as I was hinting in the previous segment, right now what we want to do is if you were given a point charge, which we kind of talked about before, or a density of charge as a function of position in a line, or a surface, or a volume, to be able to go and find either the force acting on a test charge that you're inserting or the electric field. That's where we're going to at the end of this. And so the idea is what we were talking about before, is to use superposition. And we're going to convert our summation into an integral in order to add up all of these infinitesimal charge densities. So just to do a quick establishment of the notation that I'm using. So for different types of charge, also make sure we're clear on the unit, and to get the total charge. So just as a heads up, in some cases, for some problems that you'll come across, we may not just evaluate your ability to find the force electric field. We might just say, find the total charge, and we might be good to go. So first of all, what we've been talking about before were point charges, where you just have a single charge that's charge Q that would have the unit of coulombs, and the total charge is already there, so you don't have to do any more calculation. The new thing that we're going to introduce are line, surface, and charge densities. So let's start with line charges. So this would be, you have a total amount of charge per segment of a line that you're given, and the line is infinitesimally thin. So it would have units of coulombs. So it's coulombs units of coulombs per meter. And once you figure out how many meters you're talking about, you'll get the total charge. So to find the total charge, you would take the line integral of rho L dl, and then once you integrate that through, that's kind of the same as multiplying this charge per coulombs per meter by meter, and that's how you get coulombs. Similar, you can also have a surface charge density, rho S, which would be coulombs per meter squared. And to convert that into finding the total charge, you would have to take the surface integral across the entire surface. Note that in this case, since charge is not a vector, it's just a scalar quantity. So when we're doing this ds, we had dl1, dl2, and then the unit vector normal to the surface. You can just not worry about that unit vector. Just take in the case of, say, it's an xy surface, just dx dy, do a double integral, and then you're good to go. And then finally, there's the volume integral, which would be coulombs per meters cubed. And to use that to find the total charge, you do the volume integral, as one might expect. So let's just break up the process of finding the force or the electric field into a series of steps, and these steps will just be a combination of both what we talked about before in terms of Coulomb's law, but also some of the processes of doing these integrals that we discussed in the previous chapter. So the first step, I think, is to, as with most things in life, the first step is to stop and think. So when you're stopping and thinking, what you want to get to is to choose the best coordinate system. So by the geometry of what you're talking about, you can use that to figure out whether it's best to do it in cylindrical or Cartesian or spherical. The goal is to find a coordinate system where you can take advantage of symmetry. And the second part is, once you've chosen it, it helps to find an expression for r. And once you've found r, you might as well find the magnitude while you're at it. So again, r is the source observer vector, where this is the coordinate of the observer, and this is coordinate of the source. And again, if this is your observer, this is your source, what you want is new minus old, right? So new minus old. Okay, so once you've figured out your coordinate system, come up with an expression for what the coordinate of the point that you're interested in. In many situations, you're really interested in just a specific location or a specific type of location, and then come up with an expression. So not a specific location of charge, but an expression that would describe all the charges that are in the system. Once you have that selected, the next thing you want to do is to find the unit length or unit surface or unit volume. So find either dl or ds or dv using your basic components. So using, in Cartesian, it would be dx, dy, dz. As a review, if it's in cylindrical, what would it be? Right, d rho, and then you have dz, the same, and then you have d phi, but remember, d phi by itself is not a unit length, it's just a unit angle. So to convert it to unit length, you have to multiply it by the radius. And similarly for spherical, it would be dr, r d theta, and then r sine theta d phi. So if it's dl, you're choosing one of these three. If it's ds, you're choosing two of them. And if it's dv, you just use all three. So if it's dv, it's actually easier. You have more integral signs, so it looks harder and more impressive. But in reality, it's easier because you just say, I'm just going to use all three, and you just have to choose the coordinate system. So identify your various length segments. Once you've done that, set up an expression for the electric field. So I'm just going to write very generically, the electric field is going to be equal to 1 over 4 pi epsilon naught. And over here, you would have anywhere between 1 to 3 integrals, depending on what you're given. If you're given a surface charge, a volume, or line charge, you're going to have anywhere between 1 and 3 integrals. And then you're going to have your rho, and I'm just going to leave this blank. You know, this could be rho L, rho S, or rho V. And then 1 over r squared, so r magnitude squared. So you take your expression for r magnitude that you found here and set it up. And then r hat, where this is r magnitude, the vector r divided by the magnitude. So the unit vector. Again, you know, in step 1, hopefully you found that quantity, so you just plug it in. And then the integrals, right? So again, this can either have just 1d something or 2d somethings or 3d somethings, depending on how many you have here. And then they will be, the segments will be what you chose here, right? So if it was a cylinder, then, or the toilet paper roll portion of a cylinder, so just this surface here, your surfaces are z and phi. So in that case, you would be doing a surface integral, so 2 integrals here of rho d phi and dz. So plug that in and then do the full integral, which leads into, I guess, doing the integral is kind of part of the battle, so we'll just list that out as a separate step. So integrate to find e of e as a function of r. Note that in many cases, because you're adding up all the charges, so you're adding up all the sources, so the r prime should go away because you're in many situations you're substituting, you're putting in those locations in your integration limit. So once you've integrated it, if you're adding up, say, all the charges along this cylinder, you're going to be putting in, you know, z goes from here to here, and phi goes from 0 to 2 pi, right? Those are all values that you put into r prime. So once you integrate and find the E field, the R prime should go away. Since they're all known quantities, you're substituting them with all the locations of your charges. And then finally, if you need to find the force, then all you have to do is multiply it by R, right? So multiply it by Q. So if you have a force if you have a charge Q2 and you want to say, well, what's the force? If you've already found the E field, then you just have to plug in, multiply it by Q2, and then you're good to go. Now, before we wrap up, I just want to go over, just list the formula for 2 basic situations that you might use as a starting point for calculating other quantities. So let me just, I'm going to clear out this half of the board. Here we go. The first is the electric field due to an infinitesimally thin line charge. So this is just a line charge, rho L. Let's set the origin so that it goes along the z-axis, and you want to find the electric field would just radiate outwards, right? So if you were looking at it from above, the charge would come out at you, and then the electric field would just radiate outwards in this direction, right? And in this situation, what coordinate system would you try to use? So this is a line charge, specific example. If it's running along the z-axis, that kind of tells you that it probably isn't going to be the spherical coordinate system. And then it looks the same radially, right, about this. So that kind of implies that you'd want it to be the cylindrical coordinate system. And in this case, the electric field is going to be equal to the line charge density, rho L, divided by 2 pi epsilon naught rho. So it's inversely proportional to the distance in the rho direction. So this is, we're going to go through an ugly way to derive this as an example for this chapter. And then separately for a surface charge, you're going to find, let's just keep it at the z-axis. Let's say this is kind of a surface charge along the x-plane. So charge is going to go along this way, where this is the x direction, and then the y direction comes out here. Let's give it some cool coloring here. So we have a sheet charge density. In that case, you would expect the electric field to go out in the y direction, but then at y less than 0, it's going to go in the negative y direction, right? So this is what the electric field, you intuitively would expect it to look like. So in this case, where it's kind of running along the x-axis along y equals 0, so along the xz plane, you're going to have EY is going to be, the amount is going to be rho s over 2 epsilon naught. But for y greater than 0, you would expect it to be in the positive y direction. For y less than 0, you would expect it to be in the negative y direction. So this is another special situation that you might be able to use as a starting point. So for example, if you have multiple surfaces, you might be able to break them up into individual surfaces and use this expression to come up with the solution. Similar with the line charges, if you have a bunch of different line charges, you might be able to use this as a starting point. So I just wanted to highlight these solutions that can serve as starter expressions for you to extend and solve other kinds of problems. So to review, we kind of extended what we learned about with Coulomb's law to be able to calculate the total force or total electric field for line, surface, or volume charge densities. The steps are basically adding in some of the vector calculus discussion we had into our Coulomb's law expression to convert the summation of superposition into integrals. So you identify your coordinate system, you come up with an expression for the source observer vector using, that's the step that I just erased here. But then you identify what your segment lengths are. In the case of a line charge, you choose one of these. Surface charge, you choose 2. Volume charge, you just choose all 3. Set up the equation, integrate, and then if it's the case of finding the force, you multiply it by your observer charge. And then separately, we also came up with these 2 starter equations for specific situations that you can use to solve more complicated problems later on.